I suppose it just got used to me being away. Awesome. Dirichlet, Poisson, Euler, Lagrange, Laplace, Fourier. All right. Okay, everybody. Again, today's slides are on Piazza, the latest versions, not on the course website, although the ones on the course website are not very far off from what we'll be presenting. I'll wait for one more minute and hope you all settle down. Don't forget your name tags. I will be kind towards people who didn't turn up today, who probably imagine that I'm gone forever and so not going to turn up in class. But I'm here. And so from Wednesday, I will expect everybody in class again. Let's begin. So we're going to sort of switch to our next sequence of topics, convolutional neural networks, also known as scanning for patterns. So what we've seen so far is that MLPs are universal function approximators. They can model Boolean functions, regressions, classifiers. They can be trained through variations of gradient descent, where the gradients themselves are computed using backpropagation. And so the kind of model that we've seen so far is of this kind, where you have a multi-layer perceptron which looks at an input and performs a classification, regression, or any other function that you might want to compute on the data. But then let's look at a different kind of problem. So all of you have seen Alexa, and or one of the other devices like it. You usually wake it up with a word. There's a wake up word problem. It has to recognize when someone says the word Alexa. So the way it would be done is that you have some recording. Your incoming audio is chopped up into little segments of some length. And you have to determine if the word Alexa, or in my example, the word welcome, has occurred somewhere in this recording. Now, using the technique that we are already familiar with, since all the recordings are the same length, here's what we would possibly do. I just have the collection of features, which is a spectrographic sequence of spectrographic vectors, a matrix of numbers. And I would compose an MLP that looks at this collection of vectors to determine if it has the word I am interested in it. But what is the problem with this setup? So this is a trivial solution. But then a network that finds the word welcome when it occurs in the early portion of the recording is not going to be able to find the word welcome if it occurs in the latter portion of the recording. And the reason for this is fairly simple. It is just that when you consider the entire set of inputs, you can think of the input roughly as this long vector. And when the word welcome occurs over here, just taking the extreme case, all features are binary, you're going to have zeros in all these places and ones over here. Whereas if the word welcome occurs over here, this is going to have zeros all the way until here, ones here, and zeros here. Are these two patterns the same? Yes or no? Because they live in completely different spaces, which means a network that fires for the first example will not fire for the second example unless you train it with both examples. But then there are so many different positions that welcome can occur in. So you have to have examples, training instances from every possible position. And the network too will have to become correspondingly large. This is not going to be a scalable solution. So what we need is a simple network that will fire regardless of the word welcome, and will not fire when the word welcome doesn't occur in the recording. Or here's another example. Here are bunches of pictures. Some of them have flowers, others don't have flowers. You want to have a network that can just look at these pictures and say, is there a flower in the recording? But then, so if you have a network that detects flowers when they occur in the top left corner, will the same network also fire if it occurs in the bottom right? No, right? For the same reason, right? Because they live in different subspaces. So What we need is a network that will fire regardless of the precise location of the target object. So in other words, we need position invariance. There are many kinds of problems where the location of a pattern is not important. Only the presence of the pattern is important. And conventional MLPs are sensitive to the location of the pattern. So if I've got something over here, if I move it by just one position, it's a completely different input. And so this is something that the MLP will not recognize, right? And so what we require is position or shift invariance in the network, where if I shift the basic pattern I'm searching for, the network will still fire. So how would I solve this? Anybody? How can I get a network that, or some solution that will give me an answer regardless, the correct answer regardless of the position? Yes, James?
Training on shifted versions of the data?
That's going to be, yes, that's an example. That's a solution, but what would the problem be?
Takes a lot of data.
And every possible shifted position, right? What would be a simpler solution? Yes?
You can just feed it like a shifted version of the thing, or scan. Like
Scan, right? That's a better answer. So what we want, here's a nice solution. I can build a compact little network which looks at a segment of the input that's approximately the width of my target word, welcome in this example. And then I can just scan, right? And at each position, it's going to have an output. So when this scans it, you would have classified as many windows of the input as there are positions in the input. And you're going to have an output for every position. Now, the word welcome may have occurred in one or more positions. So then how do you decide if the word welcome has occurred in the recording at all? Pardon me? That's just OR it. What is the equivalent of an OR over here? It's a max, right? I can just look at the max of these. If it has fired in any one position, then the largest output is going to be the largest output is going to be close to 1. And so the max will tell me so. If it has not occurred anywhere, the largest output is not going to be anywhere close to 1. So just looking at the max tells me if the word has occurred or not. Or, I can replace it with a soft max, a perceptron. Or if I get too fancy, I can say, I'm going to be looking at something more complicated. A minor shift of 1 millisecond shouldn't change the fact that the network fires. So I'm going to look at pattern. In fact, if you get a network that fires in exactly one position and nowhere else, that's likely to be noise. So you can take it, you can make the logic a little more complex. But nonetheless, this is the basic idea. You're scanning the input, you're putting the outputs through a softmax. So here's what it would look like if I were to write pseudocode. I'm scanning the input left to right. At each position, I'm slicing out a segment of the input. I'm putting it through my MLP. The MLP is going to produce an output at that position, and then I put the collection of outputs through a softmax. Now, but if you look at it, this is just one large network, right? I'm looking at this entire operation consists of this gigantic network, which has many subnets, all of which are identical at the lowest level, and all of which are combined through the softmax on the top. So this just happens to be, there's a specialty about the structure of the network in that all the subnets are identical, which gives it shift invariance. So in fact, I could have just taken this entire code and just call it y equals giant MLP, right? Now, same thing in the case of looking for flowers in a picture. So I could now have a little MLP which looks at a small portion of the picture and decides if there's a flower in it or not. And then I can scan the input. At each position, the network is going to produce an output. And I can just put all of these outputs through a max or a softmax or an MLP. And that's going to give me my answer. And this is going to be a shift or position invariant instance, position invariant classification of the input, right? So once again, if I were to write this as pseudocode, I'd be scanning the input left to right, top to bottom. At each position, I am slicing out a portion of the input and classifying it. Then I'm putting the entire collection through a softmax that gives me the outcome of the entire classification. And once again, this is just a giant network with many common subnets. This entire operation, this is just a very large MLP, right? All that happened was that each of these MLPs, the subnets that look at the individual windows, they're all identical. And so this is a shift invariant model, which is a single large network where all the lower level subnets are identical. And each subnet looks at a different position of the input. And so here again, I can just think of this entire thing as one MLP and just write it as giant MLP, right? So here's a poem. Ten seconds, guys. Okay. Does anybody want to answer the first question? What is the answer to the first question? True or false? True. And the second? Both are true, correct? So everybody with me so far? Okay. Now, I'm going to just use for the purpose.
Why is the second question true?
As what this is, right? This entire thing is just one large MLP.
Okay.
Correct? Yes. So now I'm just going to change my illustration a little bit for convenience. So when I showed something like scanning an input with an MLP of this kind, here's what the picture looked like. This has the unfortunate consequence of sort of implying that as you go left to right within a single layer, you're going across time. But that is not the case. Each layer is occurring at one position in time, right? The entire network is analyzing the input at one position in time. A more appropriate illustration is going to look like this, where every layer is drawn vertically. So this kind of indicates that when I show something of this kind, this entire computation is done at a single position in time. And just to simplify the illustration, I'm going to use a figure like this. It means that this is a three-layer network. The first layer has 3 neurons. The second layer has three neurons, and the third has 2. And the arrow shows all connections. So you're just going to assume by default that every layer is fully connected to the next layer. So if you wanted to see what this scanning would look like with the new figure, it's going to look like that. Everyone with me, right? And so here I'm scanning, and as I'm scanning, after each position, the network is moving forward two time steps to analyze the next position. So it's striding by 2. Instead, if I was striding by 1, this is what the analysis, the overall picture is going to look like. And then once again, you can see that although it's got its many columns which are identical, analyzing the input, the entire figure can be viewed as a single large network. But then this illustration has the nice semantic that this vertical column can be viewed as indicative of time. So now, when I see it this way, these are just really large networks, right? And if considering that this is just one large network, now I can train it. I don't need to give this network examples of the word welcome sliced out. This is a shift invariant network, which is looking at the entire input and deciding if the word welcome has occurred in it or not. And so to train this network, all I need to give is recordings with the word welcome in it and other recordings with the word welcome not in it. And you don't really need to care where the welcome has occurred. The training should still work. And this has to do with the fact that all of these lower level networks are identical. So when I train this network, if I ever perform an update to this column, that update has to be reflected across all columns because every column is identical, right? So is that making sense to everybody? Yeah.
So if you make the one giant network, would that mean you can only handle inputs of that certain length or that certain image size?
So of this length,
Right, yeah.
if you wanted to expand it further, you're just going to add more columns because the columns are identical, right? So so you're not restricted to analyzing inputs of a specific size. You could, although we will usually assume that the input size is deterministic. So everybody clear with everything we've done so far? Yes, Sergey.
Weights in between the scans, is it shared?
So every subnet is identical to, right? So whatever the weights are in this network, because this network is the same as this, they must be identical, right? Any other questions? No. On Zoom? So these are shared parameter networks. All lower level subnets are identical because all of them are searching for the same pattern. And so any update of the parameters of one copy of the subnet must be reflected and must equally update all copies of the subnet, right? So how do the update rules work? Let's consider a generic case of a shared parameter network. Let's assume that we have this network where for some crazy reason we've decided that these two highlighted connections must have the same weight. So in that case, we are going to say that Wij, which is one weight, and WLMN must have the same value, which I'm representing as W superscript S. So if I think of this in terms of derivatives, any small perturbation of this common value Ws is going to perturb both Ws equally, right? And both of them in turn are going to perturb the output Y, and they're going to perturb the divergence as a result. So if I were to draw the influence diagram, this is what it's going to look like. Here's the common value Ws. That is being shared by both of these weights which have tied values, and both of them in turn are influencing the output and thereby the divergence. So now, when I want to learn, because these two weights are shared, any update I make to one must be made to the other. So in other words, I'm not updating the weights individually, I'm updating the common shared value. So I need to know the divergence or the derivative of the divergence with respect to this common shared value. So what is the derivative of the divergence with respect to Ws? Using our distributed chain rule, that's going to be the sum of the derivatives down this path and the derivatives down this path, right? So down this path is going to be the derivative of the divergence with respect to Wij times the derivative of Wij with respect to Ws plus the derivative of the divergence with respect to WLMN times the derivative of WLMN with respect to Ws. And what are these derivatives? Anyone? 1. Why? Because it's just equality, right? You're saying WLMN is Ws, Wij is Ws. So you just end up with this derivative rule where you basically just sum up the derivatives with respect to all the terms that share the common value to get the derivative of the divergence with respect to the common value. So here's how that affects our overall training. When I have this large network with shared subnets, then there are a whole collection of edges, all of which have the same value. And so when I want to compute the derivative with respect to this common shared value, I'm going to compute the derivative of the divergence with respect to each of these guys going backwards, and then just sum them up. And that's going to give me the derivative with respect to the common value that I will use for updating my network parameter using gradient descent. And so when I'm training the network with shared parameters, the pseudocode is going to look something like this. I initialize all of my network parameters. And then there are sets of parameters which have the same value, right? Here, for example, all the edges colored red form a set which have the same value. All the edges colored blue form a set which have the same value. All the edges colored green form a set which have the same value, and so on. There are many such sets. And so for every set, we want to compute the derivative of the loss with respect to the common shared value for the set. And then you want to update that common set value using gradient descent, and then redistribute that common value to all the edges that share that value, right? So in other words, the challenge that we have is to compute the derivative of the divergence, the derivative of the loss with respect to this common shared value for the set. And for that, all we have to do is to go through every single edge in the set and compute the derivative of the loss with respect to that edge individually. They're all not going to be the same because the information flowing down the different paths is going to be different. If the word welcome occurs here, you're going to get a very different derivative from what you'd get if the word, from other places where the word has not occurred. But then you still have to sum them all up to get the derivative for the common shared value. And so you'd be computing the derivative of the divergence with respect to every element in the set and summing them all up to get the derivative of the loss with respect to this common value, which you would then use in your gradient descent rule. That clear to everybody? Right. So this is this term here. So here's the story so far. Position invariant pattern classification can be performed by scanning. It's a 1D scan for sound. It's a 2D scan for images. For higher dimensional structures, you can have scanning in 3D and so on. Scanning is equivalent to composing a large network with repeating subnets. So the large network has shared subnets, shared parameters, and learning in these networks is performed by modifying the backpropagation rules to combine gradients from parameters that share the same value. And this principle is nothing, the idea of combining the derivatives with respect to parameters that share a common value isn't specific to scanning networks, but it applies a lot to networks of this kind. Now, let's take a take a different view of the whole thing. So here again, I'm going to assume that I'm scanning the input with this network, which I will represent vertically like so as before. But the lowest level of the network is looking at a window of the input, right? So what happens when this network analyzes this window? First, the first hidden layer neurons compute their values. They are shown by these gray circles over here at that position. Then the second hidden layer neurons compute their values from the outputs of the first layer neurons. And so those are shown by the green circles. And then finally, the output layer computes its value from the outputs of the second layer neurons, shown here by this gray circle on top, or blue, whatever the color is, right? So you'd compute that in the first position, and then the network is going to slide forward to the next window and compute that column of values at the next position, and the next position, and the next position, and so on, all the way to the end. And finally, the top layer outputs are going to be softmaxed. This is the computation we are actually performing when we scan, right? But then let me change the order in which I perform the computation. So here, as before, the first layer neurons compute their outputs at the first position. But then instead of waiting for the rest of the network, they go off and wander off and perform their computation all the way to the end. Then the second layer neurons, which were lazy and hadn't yet gotten to class, finally make it to class. And they compute their outputs from this first column of the rest of the network, computes their outputs from this first column of outputs. So when this happens, will the final output here be any different than what you would get if the entire network analyzed the first window? No, it's going to be the same, right? And so, but then look at what's happened. Let's say that the different layers are staggered in their sleep cycles, right? The first layer has come, performed its scan, it's gone back home. Now the second layer arrives, and it goes ahead and computes it, because all the first layer outputs are already available, right? The second layer can go ahead and compute all of its outputs all the way to the end. And then Mr. Output layer arrives, and he computes his output from these values. Will the value be different than if the entire network had analyzed the first window? No, right? And so this final layer can perform its scan on the outputs of the second layer, and then you can have your softmax, and you're guaranteed that the final output is still going to be the same. All they did was reorder the computation, right? So in terms of code, what happened over here? Here's what I had earlier. I had this input. You were scanning the input. At each position, you are segmenting out a little segment and passing it through the network. Let me expand that out. So you are scanning the input. At each position, you were going through all the layers. The first layer, from the first layer to the output layer, the first layer looked at a chunk of the input, and then the remaining, and then every layer sequentially first computed an affine value from the output of the previous layer, where the 0th layer is just a chunk of the input. And then we applied an activation to it, right? So here, the outermost loop, the way we did it, was over time. And then at each position, you were looping through the layers. But all the main computation is being done within the innermost loop, right? If I flip the order of these top two guys, well, is it going to change the final output? No, right? And so that's basically what we just did when I reordered my computation. I just flipped the order of the top two guys. So same thing over here. If I was scanning the input with the network, with this network, then at each position, that network is going to be producing a value, right? So as the network scans the input, it's going to compute one value at each position, which I'm arranging in the same order as the scan. So the output is going to be proportional in size to the input, right? And then that's what you'd put through a softmax, that entire collection. But then let's reorder our computation. This first neuron arrives to class first, and then he goes off and performs his operation. In fact, he has a study group which consists of the first layer, so all of them arrive and they go through the input and scan it. And each of them arranges their output in the same shape as the input itself. And now the rest of the network arrives. And they, in order to compute the output at this position, they pick up the values that all of the first layer neurons computed at that position and compute their output. Is the output going to be any different than if the entire network had just looked at that window? No, right? And of course, you can recurse this, right? The second layer neurons can now scan the outputs of the first layer neurons. But look at what's happening over here. The first layer neurons scan the input. The second layer neurons are scanning all four outputs, the outputs of all four first layer neurons simultaneously, right? That's what they will have to do to get the same computation as before. But then they can scan those simultaneously. And then in order to compute the output at this particular position, they can just read, the output neuron can just read the values that they computed from the corresponding positions in the outputs of the first layer neurons, which in turn were derived from this box. And this output is guaranteed going to be the same as what you would have got if the entire network had just looked at that window, right? Everyone with me? Okay, no questions, right? So now, if I want to detect a picture anywhere in the window, and then I can do the same thing as for the output neuron as well, which can now scan the simultaneous. Yes.
So for the, can you explain again like the second layer? I'm confused as to how it's like equivalent. Like I don't understand like that visual in reference to.
Okay, let's go back and look at this guy, right? If I were computing.
Yeah, I get this, the first layer visual. I don't get this.
Okay, the second layer visual, right? So this is easy. Now suppose I want to compute the output of the rest of the network, or compute the output of the entire network. for this window.
Okay.
All I have to pick up is the outputs of the first layer neurons when they were looking at that position, right?
Yeah.
So that's about it,
I see.
right? And so look at the red box to the left and what's happening here. There are two things moving, right? At each position, you're just picking up the outputs of the first layer neurons at that position, and you're going to get the output of the second layer neurons for that position, right? Yes.
Is the value making and showing us a value we can swap the loops so we can run this in parallel, or what's the value?
Hang on with me, right? We haven't gotten to the end of class, right? Yes.
Are there 4 outputs? I mean, in the first
4 neurons, right, in the first layer?
Yeah, but they're all computing mathematics.
Okay, no.
Are they? Right, okay. So now, so if I want to detect, so the final output neuron layer can also scan the second layer outputs. And now if I want to find out if there's if a flower in any position in the input, I just have to read the value computed by the output neuron at that position. Bishop, do you want to go out for a coffee? No, okay. I know it's Monday and we're all sleepy and but bear with me. I'm sleepy too. I'm jet lagged. Okay. So, and of course, the entire thing can be passed through a softmax or a max. Nothing changed. So when you're doing your homeworks, you will see this little thing called flatten, where you'd like to take the output map and make it a vector. That's just an engineering artifice. It doesn't bother us. But then from the perspective of what we are doing, so here's what we had. You are scanning the input left to right, top to bottom. At each position, you're slicing out a segment and analyzing it through the MLP. So this inner portion, for the segment, you are going through the layers first to last. The 0th layer is basically the input. And then at each layer, you computed an affine value from the specific inputs, specific values for the previous layer, and then applying an activation to it. So here, this entire operation is occurring inside the innermost loop, right? So if I flip the order and move the XY inside and the L outside, will it change the overall computation? It won't, right? And that's basically what we just did. So here's I can write the whole thing in vector format just for notational convenience. We'll skip the details of it. Just take a look at the slides. So position invariant pattern classification can be performed by scanning the input for a target pattern, which is equivalent to composing a large network with shared subnets. The operations in scanning the input with a full network can be equivalently reordered as scanning the input with individual neurons in the first layer to produce scanned maps of the input, and then jointly scanning the maps of, or the output maps of all the neurons in each layer to produce the outputs of the next layer neurons, right? So, any questions? Because this was the easy bit. We were just waving your hands and legs before jumping into the pool. Right, let's jump. But there's a pool. Seconds, guys. This was easy. You should be done. All right. What's the answer to the first question? Someone on Zoom. What's the answer to the first question? Anyone answering? True. Okay. And what about the second question? What's the answer? Right? Can you be a little more enthusiastic for my sake? Please, right? Okay. So they're both true. Now, there's something off. My slides are not updated. But anyways, damn. So I'm going to be showing you slides which are one version behind from what's on Piazza. It doesn't matter. Okay. Now, what we had was that the entire MLP looks for a flower-like pattern at each position. So in the manner in which we computed things, these first layer neurons looked at the entire window of input, right? Subsequent layer neurons looked at only one position in the maps of the previous layer neurons when you scan the whole thing. But then this places the entire responsibility of analyzing the entire window of input on the first layer neurons. They are sort of given the responsibility of looking at everything and figuring out what's going on. Now, I can sort of share the responsibility over multiple layers. What would I do? Instead of having the first layer neurons look at this entire box, the first layer neurons can look at a smaller box of this kind and produce their maps. Just scan the input and produce their maps. Each neuron is going to produce its own map. And then the second layer neurons can now look, because I'm arranging the outputs in the same pattern as the input itself, the second layer neurons can now look at a small window of the output of the first layer neurons. But in so doing, what happens? This neuron is looking at these 9 positions over here. So it's effectively looking at the total position, the union of all the positions of the input looked at or evaluated by the 9 neurons, right? Which is going to be this window over here. And so now the second layer neuron can actually, what this does is it sort of distributes the pattern matching over 2 layers. And you're still going to achieve the same block analysis at the second layer. So the first layer is not evaluating smaller blocks of pixels, and the second layer evaluates windows of outputs in the first layer, and so it effectively evaluates larger windows. But then what does this gain us? Instead of saying the first layer neurons are going to look for big flower-sized patterns, you can say flowers have things like sepals and petals and such like, which have very great similarity, right? So the first layer neurons can look for things that look like sepals, maybe. One of them looks like for small sepal-like patterns. Another looks for petal-like patterns. And then the second layer neuron can say that if this first neuron finds patterns in these 2 positions, and the second neuron finds a pattern position here, and the third one finds a position here, and the fourth one finds a pattern in this position, that combination determines the presence of a flower, right? So you can actually look for complex patterns over the smaller patterns evaluated by the lower level you can look for complex arrangements of the patterns detected by the lower level neurons. And so the second layer neuron can now scan the maps produced by the first layer neurons. And they effectively scan the input with the full-sized window. Except, of course, when the second layer neuron scans the maps produced by the first layer neurons, it's jointly scanning the maps of all the neurons, as always. So it's all, it makes sense. That's what all of the arithmetic we've seen and so far pictorially tells us we must be doing, right? And now, to compute the output of the MLP for some window of the input, the final output neuron only has to look at the output of the second layer neurons when at that position. And so it can scan, right? And it can scan, this guy can just jointly scan the outputs of these 2 neurons, and it's going to get the output of the flower detector for every position in the input, which you could put through a softmax. But then, you may have distributed patterns over 2 layers, but this is still just scanning the input with a shared parameter network. Nothing changed. Something changed, but it was subtle. The overall the overall structure didn't really change very much. So what is the minor modification? Earlier, we had all of these subnets which are identical, and their outputs were being put through the final MLP or softmax, right? But now, if I have a network of this kind, where the lower level neurons are looking at small boxes, and the second level neurons are looking at windows of 3 cross 3 in the outputs of the first level neurons, it means that this second level neuron is considering the output of these neurons at these 9 positions, right? It's considering the output of the red neuron also at these 9 positions. It's considering the output of the blue neuron also at these 9 positions. And at all of these 9 positions, the black neuron had exactly the same parameters, right? And so when you look at the overall structure, the actual network, which I drew very simply over here, has this structure where there are 9 copies of this first neuron looking at these 9 positions. There are 9 copies of the second red neuron also looking at these 9 positions. And there are 9 copies of the blue neuron also looking at these 9 positions. So the parameter sharing has also occurring. Not only is this overall network identical at every position, within each position, you have local parameter sharing, where the 9 copies of the blue, black all share the same parameters, and so on. That making sense? Eric, I see a question on your face.
It's just hard to picture with the earlier model. It's hard to put the two together.
Any confusion here? Yes, Sergey.
Pretty much the same question. I'm trying to understand how this constitute parameter sharing in this.
So look at these 9 guys, right? They're all this one looking at a smaller window, going left to right, correct? Yeah. So all of these are 9 copies of this neuron. So this one is this neuron evaluating this window, right? So there are 9 copies of the neuron. That's parameter sharing, right? Make sense? Anyone else?
Does the black neurons and the red neurons also share weights?
So this is basically this black neuron scanning this in this local region, right? So it's the same thing. It's 9 copies. The way to see it is 9 copies of it, right? And now I can build a pattern over 3 layers in the same manner. The first level neurons could be looking at something really small, like this, right? Then the second level neurons could perhaps be looking at 2 cross 2 in the maps of the first level neurons. And what are they looking at? Now each second level neuron is now looking at a region that size. And the third level neurons can now look at a window of the output of the second level neurons. And effectively, what are they looking at? Each second level neuron is looking at a 2 cross 2, right? So this guy is actually looking at this larger window. And so I'm building the pattern over 3 layers to perform my classification. That each dot in the final layer is actually looking at that at a full size window. And I'm actually still just scanning the input with an MLP, right? So the final classification of the entire image simply views the output of all locations as seen in the final map. But then this didn't change things. We are still scanning the input with a large MLP, except that now you have parameter sharing at every level of the network. Just as when I distributed it over 2 layers, I had parameter sharing in the first layer of the network. When I distributed over 3, I have parameter sharing in the first and the second layers. But otherwise, nothing really changed. You're still scanning the input with a large MLP, but then the MLP itself has locally shared parameters. Make sense to everybody? Right, yes.
People are asking what's the difference between the black, red, and blue neurons in the network.
So there are just 3 neurons. Here in this case, I had a first hidden layer had.
Apparently, how are they different? Why do we need the, and what are the 3 neurons looking for in the network and how are they different?
So these are, each of these, the black, red, and blue neurons all have different parameters. So just as this is no different from when we went back all the way here, where we had 4 neurons in the input, right? And each of the neurons was looking at a large window, the same window. Does this mean all 4 neurons are identical? No, because your hidden layer is looking at the all the neurons in the hidden layer may be looking at the same input, but they're learning different things, right? So that's the same thing happening over here as well. There was another question. What was that? Yeah.
I'm still confused on the concept of parameter sharing.
It means that all of these guys have the same parameters. So if you make an update to the parameters of this copy, you must update all of these copies. That's all.
And then how is it that, because I thought in the slide it mentions that the second layer, there's no sharing, but then you mentioned that there is. Like,
No, I'm saying that over here there is none, right? But then if I distributed this across 2 layers,
okay.
then there would be.
Oh, so it's only at the it's everything until the last layer. There's parameter sharing.
Yeah. Right? We'll see some more figures, which makes it wildly clear, right? So this is still shared, these are still shared parameter networks. So if I look at it from the perspective of pseudocode, what happened over here? It's I have a k cross k size window analyzed by the MLP. Now originally I was scanning from left to right, top to bottom, right? And I was slicing out a segment of the image and putting it through my scanning MLP and then combining the outputs. But then let me expand it out. This is without distribution. This is what we did earlier. So for the first layer alone, I sliced out a window of the input. And for the first layer alone, the affine value, so y0 was a slice of the input, right? For the subsequent layers, it was just one position of in the maps from the previous layers. And so if I had to write pseudocode, I had to say for the first layer, at the input, take a region from x to x plus k minus 1, y to y plus k minus 1. So it was a little window, right? And that was what was being used as my segment. Whereas for subsequent layers, I was just picking the value at one position. So I had this extra bit of logic, and then I was just computing the z value from the segment and applying the activation. And we reordered that. So we pushed the computation over layers on top and the scanning down below. But now I can do something else. Instead of saying that the first layer alone looks at a window of the input, I can say every layer is going to segment out a little region from the maps created by the previous layer. So this is actually, in terms of code, this is more uniform. I don't have an if clause for the first layer. And then I'm just going through the inputs and computing the affine values and the activations. So code-wise, you can see that this is actually simpler. It may make more sense to some of you guys, right? Now this business of taking a segment from the input and applying a filter to it and then scanning the input with this filter, with this set of weights, is what is called convolution. And which is why this entire operation is called a convolutional neural network, because you've got this neurons which basically are looking at regions of the input and they're scanning the maps of the previous created by the previous layer neurons. So this business of applying a filter to a window and scanning the input with a filter is called convolution. So this is called a convolutional neural network. By filter, I mean the set of weights that the neuron has. So again, I have this in vector notation. Let me skip it. Now, the 1D scan version of it, I showed this using 2 dimensions. But then illustration-wise, I don't know which one makes more sense. So let's take a look at what would happen in 1 dimension. So here, I would have maybe a recording of this kind. I have a network, which I've drawn vertically, right, as before. And so I'm going to be each neuron in the first layer can scan the input like so. So the set of all the neurons in the first layer would scan the input. But then look at what's happening. Every one of these neurons is looking at a small window of the input, right? But then the second layer neurons I want the second layer neurons to actually capture a larger region of the input. And in order to do so, they're actually going to look at a small window of the outputs of the first layer neurons. And that's going to give you a larger window. And they will scan the output in this manner. So in other words, the second layer neurons are scanning the outputs of the first layer neurons using a window of that width. At each position, all of these 12 values will be used. Each of them will have a different weight, of course, right? And so that's the combination you're going to be using to compute the outputs. And of course, each of these neurons will have a different set of weights in computing these outputs. And now, if I want the final layer neuron to look at a pattern that's about the width of by word welcome, then it means that it actually has to look at a window of outputs for the second layer neurons, and then it has to scan the outputs of the second layer neurons like so to get the appropriately sized window from the input. So, and the final perceptron or MLP will aggregate the evidence for does this recording have the word welcome in it. In the case of one-dimensional convolution involving inputs in this manner with a distributed network, this is called a time delay neural network as opposed to a simple convolutional neural network. There's terminologies that I'm trying to get you familiar with. Yes?
Will convolutional neural networks struggle with different size images of flowers, like if a flower is very small versus very large?
Scale issues, we'll get to that in a couple of classes. Yes? Yes. There isn't a wide, they cannot deal with a wide range, no. Unless, of course, they learn all of them. You know, there's massive amounts of data thrown in and always learn something. Yeah. When we were doing this, right? Yeah. So when I say distributed, I'm saying I'm distributing the pattern over many layers, as opposed to having the first layer look at the entire input and the rest of them to perform spot analysis. Okay, so I've used up too much time. Does anybody on Zoom want to answer the question? Anyone? Zoom is awfully quiet.
This is B and C. 2 and 3.
2 and 3, right? Everybody with me? Right. Okay. So now, why bother? That's to answer James' question from very long ago, right? Why all this drama? There are 3 reasons. First, if I just look at have the first layer neurons look at the entire input, and then subsequent layers look at just one value from the outputs of the previous layer neurons. That is forcing the first layer neurons to capture all the patterns, and subsequent layer neurons are just sort of building on the extra work done by the first layer neurons. When you distribute this representation over many layers by having the second layer neurons look at regions of the maps produced by the first layer neurons, it sort of forces hierarchical representations with localized patterns in lower layers. Also, this distributed computation, we will see, results in fewer computations because we have reusable computations from lower layers and far fewer numbers of parameters. So let's see what this first thing is all about. For the first thing, let's harken back to several classes, right? Here, remember, when we looked at this double pentagon example, we were not trying to force the first layer to learn the entire pentagon and the rest of it to capture it. Yes, sir.
I still don't quite get the notion of distribution in this sense. Like, is it? Yeah, it's basically like the core notion of it. What is distributing the scans?
So let me go back all the way here.
Yeah.
That's okay, right? When we did this, going back here, which layer looked at the entire input? What about the second layers? It looked at just one position. There was no, it had, the entire input was already considered by the time the second layer was analyzing the input, right? So this entire region is being captured by the input, and the rest of them don't really have spatial work to do. Whereas when I do something like this, right, using a smaller input, then the first layer neurons are only looking at a small region of the input. But the second layer neurons are looking at a region of the first layer input. So now that region, this square region, is being distributed over 2 layers.
Okay. So you're basically distributing the load of the content.
Distributing the region that you're analyzing over many layers. That makes sense?
Yeah.
Correct? So that makes sense to the rest of you had doubts over here, right? So, and over here, so here, for example, doing that gave you the advantage of saying that, you know, you want these guys to fire from the different first layer neurons, and that should find you the pattern. And then when we had the second layer neurons look at a region of the first layers, the third layer neurons look at a region of the second layer neurons, which in turn were looking at regions of the first layer neurons. You were distributing this region over 1, 2, 3 layers, right? So, and let's go back and see why this works. First, when we were looking at the double pentagon, what would have been the problem if I just let the lower layers try to capture the entire pentagons? How many neurons would I have required? An incredibly large number, right? By distributing the patterns over more layers, I just ended up with a much more compact network than to do the same job. It was much more efficient. So what happened was I had this complex pattern, but the lower layer neurons just got local patterns, just the edges. The next layer neurons caught little pentagons. Then the final layer combined them up. Or when we were doing something of this kind, you didn't say that I want, if I'm trying to find out if the input is a digit or not, I didn't have the first layer simply try to detect all the digits. You can do that, but it's going to be more complex. Instead, the first layer maybe found the little patterns that compose digits. Then the second layer composed the digits, and then the final one said, is this a digit or not? And this is more efficient, right? So in general, we want to encourage such hierarchical learning of the model, because that's going to make it much more efficient and much more effective. There's a reason we want to do this. But the second and third are also equally, if not far more important in this particular setting. Far fewer computations, because you're going to reuse computations from lower layers. And to see how, I'm going to use the 1D scan. 1D scans are easy to visualize. In 2 dimensions, they're kind of more painful. So let's say I'm trying to analyze an 8 frame or 8 vector, 8 time step region of the input to detect the presence of the word welcome. Is this a distributed scan? No, why is it not? The first layer is looking at the entire input, right? And the rest of them are just feeding off the work done by the first layer. So here, if you scanned it, this is what the structure is going to be like. Okay. Now, no computation is shared across columns. Every column does its entire computation, right? Reordering the computation buys you absolutely nothing, because the same amount of computation is being done either way, right? So I'm going to just use these simpler boxes rather than draw the individual neurons, because it's a simpler illustration. And now let's assume that I have N1 neurons in the first layer, N2 in the second, N3 in the third, and I have a width of 8 that I'm looking at, and each of them is a vector. So let's say that the dimensionality of the vector is D, right? So how many parameters will I need? I have N1 neurons. Each of them is looking at 8D inputs, correct? So I'm going to need 8D N1 parameters for the first layer, N1 times N2 neurons for the second layer, N2 times N3 neurons for the third layer. This is the total number of unique parameters. Now, and you need to only compute them for one column because all the columns are identical. You're just scanning, right? So this is the total number of parameters. This is just a generalization if you're looking at a width of L, okay? But then let me convert this to this network. The 8 yellow boxes, the yellow boxes are all identical. Is this a distributed network or not? Yes. Right? So I have the same network looking at different regions of the input. It's looking using a stride of 2. The next layer is aggregating the outputs from the first layer neurons and then passing it on, right? But then each of these lower level guys is only looking at 2 inputs. But how much is the overall network looking at? 8, right? It's no different from this guy, right? And so now, if I were to compute the number of parameters used by this one, how much is it? How many parameters does this? So let's say each of these is, there are N1 neurons here, N2 neurons here, N3 neurons here. And this is, the depth of this input is D. How many neurons will the first layer require? 2D N1, because the 4 copies are identical, right? What about the second layer? 4 N1, N2, because it's looking at 4 vectors from the first layer, 4 N1, N2, and the third one is N1, N2, N3, correct? Everybody see where these numbers came from, right? So it's going to be 2D N1 plus 4 N1, N2 plus N2, N3, right? So those are the unique parameters. And so that's where the count comes from. Now compare it to what you would have if I didn't distribute. If I had the same number of neurons, then instead of having 4 N1, I'm going to have four bars of size N1. I'm going to have 1 bar of size 4 N1, right? To have the same number of neurons in both cases. But then if I did so, I'm going to have 4 N1 times 8D, right? That's going to be 32D N1 plus N1, N2 plus N2, N3, as opposed to 32D N1 plus 4 N1, N2 plus N2, N3, as opposed to 2D N1 times 4 N1, N2 plus N2, N3. So there's a factor of 16 that disappeared in the lowest layer, right? So now let me try, and so when I'm actually performing the computation, the width of 8 is now distributed over 2 layers. And if I was striding by 2 steps at a time, this is what the computation is going to be like, right? Now, observe something. When I go from here to here, when I go from this position to this position, how much extra computation am I doing in the first layer? 1 bar, because 3 bars are being reused, right? So in terms of computation, how much extra computation did I get? Just 1 extra bar, right? All the reuse means that in terms of compute, this is going to be way, way, way faster than having the undistributed network. Make sense? Right? All of those guys are going to be reused. Now, here's another one. Taking it one step further, I'm distributing it over 3 layers now. If I did so again, these guys are looking at 2 inputs. The next layer neurons are looking at 2 inputs from 2 bars from the previous layer. And the next one is looking at 2 bars from the previous layer also. So what is the final width that the network is looking at? 8, right? No different than before. But then how many parameters do I have? What are all the unique parameters? This guy is, these are unique, right? So also these are unique because this is identical to this. And these are unique. So how many parameters will I have? Somebody want to answer me? I'm going to pick someone if nobody wants to answer me. So Sanjana, what's the?
So for the first layer will be 2D1,
Mm-hmm.
there will be 2 N1, N2 because 2 blocks.
Mm-hmm.
Third layer will be 2 N2, N3.
Perfect, right? So whereas if I wanted to have an undistributed network with the same number of neurons, then does somebody else want to tell me how many parameters I will have? I can pick somebody. So Josh. How many parameters will this have? Does somebody else want to answer? Is 32N1 plus 8N1N2 plus 2N2N3. So compare these two, right? And you can see that you're getting a factor of 16 in the first layer, 4 in the second layer. The number of parameters just shrinks rapidly as you distribute the network, the feature over more and more layers, right? In terms of reused computation, if I'm doing this again with a stride of 2, look at all of the computation. So when I go from the first position to the second position, I'm only going to be computing 1 extra yellow bar at the bottom, right? So if I look at the first and the third position, these guys are being reused and these are being reused. If I look at the first and the second position, then these 3 are being reused. There's a whole lot of reuse of computation as you go from bottom to top. And so you're going to get orders of magnitude reduction in the computation as well. As Sergey?
In the non-distributed net, how is the output of first layer 4 and 1?
For this one, so I want the number of neurons in the 2 networks to be the same, right? Otherwise, comparing networks of different sizes is not fair, is it? So you're going to have a lot fewer. These are the unique values, and so you can see the things that the computation is being reused. And I can draw the same figure for the 2-dimensional scan as well. And in the case of the 2-dimensional scan, so as I go, so consider, say, this neuron scanning a box of that size. As I go from one position to the next, these 12 guys are not going to be recomputed, right? They're reused. So if I were not distributing it, I'm going to be computing this entire box every time as I move forward. But because I'm distributing it, I'm only computing 1 extra column as I slide forward every time I go forward. And so you can see once again that you're going to be reusing a lot of the computation. And moreover, when you actually look at the web parameters, you're going to use far fewer parameters. So I have some numbers over here, but they tend to be boring. So let's not look at numbers. No. Yeah.
Just a quick question. Is this done internally in libraries like Pythons? Like, do we really reuse computations when we are doing convolutions?
So do you really need, so here is the thing. You don't explicitly do it, right? Here's the beautiful bit. Look at what happens. I just computed this entire collection. I'm not going to recompute it again. Now, as far as I'm concerned, the next layer is only looking at the sequence of bars. So it's effective, the same bars are being used at different positions, correct? So the computation is just reused. You don't have to explicitly do it. It just happens, right? So let's move on, right? If you actually, the math is there on the slides. One thing I would want you to keep track of, every neuron has a collection of weights and a bias, right? So in all of the computation over here, I sort of ignored something. And what was it I ignored? The bias term. You will have to be careful. So when you do work out the arithmetic for the actual numbers, you'll have to either factor in the bias or just live with the assumption that your network never uses a bias. Yes?
Does it have like different outputs for 2D
So yeah, they got, I mean, so in the non-distributed one, look at this. This guy is going to be looking at this entire input, right? So by the time you get here, do you think these two outputs are going to be the same? Because this is assuming that that you have shared parameters at the lower level. So the outputs will be different. The computations are different. You're performing fewer computations. You cannot expect the same outputs, right? So questions, anybody, before I go on?
Yes. So in shared parameter networks, once we compute the derivative with respect to common weight, how do we redistribute that?
So you know exactly which set. Okay, if you're scanning, you just have to update the one copy that you're scanning with, right?
But then each neuron would like have a different weight, right? Contributing to the common.
So at each position, you're getting a different derivative.
Okay.
And the derivatives are being aggregated, right? And that aggregated derivative is being applied to the neuron, which is scanning. Right, so it's convenient to think of it as a network or a neuron or a small layer that is scanning. And so at each position, it's computing some derivative. All of these derivatives are being aggregated, and that's being used to update the layer itself, which will then scan again at the next time. Does that make sense? Okay. Oh gosh, okay, yeah, poll 4. You didn't see the answers, guys. The poll not showing up? It should be up now. So here's the magic. I don't know if you realize we just went through 270 slides. The poll not showing up still? All right, okay. We'll live with that. Does anybody want to answer the question? Chantal, can you answer the question?
I think
The first three, okay. Laksha? She's a very fast reader, but yes. Okay, the first three, right? So the number of intermediate memory variables doesn't change, right? You're not saving anything in terms of memory, you're saving in terms of computation.
Parameters-wise, you're also saving it, right?
In terms of parameters, in terms of the intermediate variables like the affine terms and activations and affine values are going to be the same. So now some final touches: terminology, filters, receptive fields, shrinking the maps, accounting for jitter, pulling, right? So here's the entire operation that we were looking at again. It can be redrawn as maps of the entire image. Each neuron scans and redraws the input with some features enhanced. So you can think of it as saying that the first layer neurons are looking for some specific patterns in the input, and they're looking at the inner product between the weights and the pattern, right? And if that weight pattern exactly occurs, the output is going to be high, otherwise it's going to be low. So you can say that the first layer neurons are enhancing specific patterns in the input. They're basically repainting the input, right, with some patterns enhanced. So, and that's, if you actually visualize their output, that's pretty much exactly what's going to happen. And say these could be, so they'll be looking at sub-regions of the input, say sufficient to detect a petal, and it's going to say, okay, petals have happened. The second layer neurons are going to look at regions of the output of the first layer neurons, and they're sort of putting these petals together into something like a flower. This corresponds to looking at a larger region of the input image. And so they're scanning the input now effectively with this larger image, right? And the third layer neurons are going to be looking at regions of the second layer neurons. You can have several layers of this kind, yes.
In the previous poll, the answer says that the benefits of using distributed model can it enables hierarchical composition of patterns. So can we say that non-distributed model cannot apply hierarchical composition?
Yeah, they are not, because there is no hierarchy, so they will not look at it, right? They're not, if the model itself is not inducing hierarchy, it will not find a hierarchical structure. You're not putting patterns together. I mean,
Well, I think if we're stacking layers, then it can perform that.
so again, the input layer is looking at the entire pattern. So while the subsequent layers could be looking at, putting together patterns found at the input, yeah, there will always be a hierarchy in that sense, but it's not enforced, as in the case of the distributed models, right? You're always looking at full structured, full-sized inputs, as opposed to putting together smaller patterns. So now, each of the scanning neurons that we looked at has a name. The set of weights is typically called a filter. I use this terminology. This comes from signal processing. You're scanning with a filter, that is convolution. But basically, the way to think about it is that the set of weights is looking for specific patterns. We saw that the inputs, the neuron is most likely to fire when the input looks exactly like the weights, right? So the set of weights of each neuron represents a pattern that the neuron is looking for and is going to highlight. So that's called a pattern. And the pattern in the input that each neuron responds to is called its receptive field. So for the first layer neurons, the pattern of weights itself is the receptive field. This is the pattern that it's looking for. The second layer neurons are putting together stuff from the first layer neurons. So it's not really very clear what the receptive fields must be or can be, so they must be computed. They may not be simple and identifiable patterns, like this is capturing petals and these are capturing sepals and so on. And generally, in your standard, if you're doing your homework, the output of the final layer is going to be reorganized into some kind of a vector, which is this operation that I mentioned is flattening. Now, there are some minor modifications. In all of the figures that I showed, I assume that it's just striding forward by some amount. What is the stride? It could be 1 pixel. It could be a collection of pixels. So there's a notion of stride, which is a parameter that we would often have to choose, and that's just going to modify your code by how much you're going to shift when you're scanning. There's the other more important thing. Suppose my first layer neurons are looking for petals, and the second layer neurons are looking for combining these things. And if I say my petal moves a little bit, did that stop being a flower? Should I reject the pattern? No. There's a small amount of variation that you want to be tolerant to, right? So we want to say that in the lower layers, regardless of whether a pattern occurs here or here, I still think I'm just going to key in on the fact that the pattern occurred. And so the way you do it, you can just as we are using this max in the final layer to say, I'm going to fire regardless of where the flower occurred, I can go back to the early layers and say, I'm going to let it fire regardless of where in this region the sub-pattern occurred. So this is called pooling. And so what we would do is sort of look at regions of the input and pick up on whether the pattern we are looking for occurred anywhere in the region. There are a couple of different ways of doing it. One is called max pooling, where you just look at a region of the input and pick up the max value, just as we did at the final output. This is again to account for jitter. And so max pooling would scan the input with, I don't know, some figures are missing. Alternately, you could use the mean, which is called the mean pooling, We'll look at more of these in the coming class. Today's class was all about sort of introducing the overall concept that what we are really doing is scanning for patterns, right? The convolutional neural network is a network that scans for patterns. Mathematically, that's the way to think about it. But in the next class, we are going to talk about all of these from a different perspective, which is a biological perspective. Start off with a biological model, which is where convolutional neural networks were originally introduced from. And we will revisit all of these, but from a different angle. So for today, the story, neural networks learn patterns in a hierarchical manner, simple to complex. Pattern classification tasks such as, does this picture contain a cat, are best performed by scanning for the target pattern, and scanning can be viewed as classification with a large shared parameter network. scanning an input with a network and combining the outcomes is equivalent to scanning with individual neurons. First level neurons scan the inputs, higher level neurons scan the maps formed by lower level neurons, and a final decision layer simply makes the final decision. And the scanned block can be distributed over multiple layers for efficiency. At each layer, a scan by a neuron may optionally be followed by some pooling to account for jitter invariance. And for two-dimensional and higher dimensional scans, this structure is called a convolutional neural network or a ConNet. For one-dimensional scans, we call it a time delay neural network. I'll see you in the next class. Yes.
So until now, for some reason, I didn't say, looking for